Last example. This one will definitely require some thinking. So we'll start off thinking about the problem and then actually approaching it, which is a great way to approach your problems in general. Think about it, then approach it, then actually do the math. So we've got two blocks of masses m1 equals 2 kilograms and m2 equals 1 kilogram. They're sitting atop each other, and they have a coefficient of friction, mu static, equals 0.7 between them. The bottom block is resting on a horizontal, frictionless surface. What's the minimum force to keep the top block from slipping? All right, so first of all, if they're moving at the same rate, what does that mean? Well, then that means that we've got some a1 acceleration, and we've got some a2 acceleration, right? And they're both going to be moving in the direction of force. So these are our accelerations are going to be going this way. But what about the fact that if they had different accelerations? Well, what would it mean if they had different accelerations? If they had different accelerations, then one of them's either going to be sliding off of the other or, sliding behind the other. There's going to be a difference in their relative velocities, which means that they have to have, they can't be staying together anymore. It has to be slipping by the definition of slipping. So that means, just to begin with, we know that the acceleration of the first block has to equal the acceleration of the second block. So we can just call them, in general, A. So the accelerations are equal between the two. All right, what else do we know about this? What keeps block 2 on top of block 1? Well, there's no forces that we're putting in externally. There's nothing on it. The only force that's keeping it there is the force of friction. M1 is moving this way. So that means that for them to stay attached, static friction wants them to stay in place. M2's friction is going to pull this way. So we've got friction moving this way. And, I just drew these in. These are the same thing. So friction is going to be pulling block 2 over. What about block 1 will result in force? So M1 is going to be reduced by that same friction. These will be equal. Equal in terms of magnitude, not direction. So M2 is going to be accelerated by friction. M1 is going to be decelerated, or at least lose some of its force to friction. All right, so that gives us an idea of what we're actually doing here. We've got these two blocks. They're pulled along. Only the bottom one is being pulled along. And the way that it's able to communicate to the top one, the way that it's able to cause it to move, is by using friction. The bottom one and the top one, they only communicate through friction, so friction has to be the thing here. If we're able to put so much force, and this makes sense, I'm sure you've seen it, if you've got two books on top of one another and you yank the bottom book really hard, the top book will just fall down. Whereas if you yank the bottom book slowly, you don't yank, you pull gently, they'll both slide along easily together. This is going to be connected to the coefficients of friction and the masses of the books. All right. So what's going to be that minimum force to keep that top block in place? Well, I'm sorry, what is the minimum force to cause it to slip? What is the maximum force to keep it in place? There'll be the same thing, is it's that razor's edge once again between slipping and not slipping. But now we've got the understanding to actually approach this problem. All right, so final thing, now we can actually do the math. So let's start looking at the two free body diagrams. So in this case, we've got some force, right? What else is operating on it? Well, we've got friction from the top. What about its own friction? Does it have its own friction from the ground? No, remember we said that it's on a frictionless surface. So in this case, there's only one friction. There's just the friction between the blocks, right? Between the blocks is the only friction. Okay, so what is mu s? We know mu s. What's normal force? Well, how hard does M2 push in? M2 is going to push in with M2 times G. So Fn equals M2 times G because it doesn't burst through the box. It doesn't move through it. It stays on top of it. If we just let it alone, it would sit there. So that means that the normal force has to equal M2 times G. All right, so with this in mind, we can start coming up with our formulas. So net forces, we know that F will make this the positive direction. We know that F minus friction equals the mass m1 times the acceleration, right? And we could, we'll make these all vectors, but it doesn't really have to be because we understand the directions because they've been dealt with. So technically this one can't because it's a minus here and we have positive, but anyway. So F minus friction equals M1 times A. What is the forces on M2? Well, just friction equals M2 times A. All right, well, with that in mind, we can start to figure out what is F going to have to be equal to. So, well, F, we sub this in, we get F minus M2 times acceleration equals M1 times acceleration. So we've got that the force equals M1 plus M2 quantity times the acceleration, right? So that's how much force is necessary to give an acceleration to this, because it has to move both of the objects. It has to move the whole system. All right, we can sub that back in though, and we can now figure out what is friction. So F over M1 plus M2 equals the acceleration. We plug that back in to this formula right here, and we get that the friction is equal to M2 times F over M1 plus M2, getting a little cramped there. So we've got that friction is equal to the force M2 times the force over M1 plus M2. So now we could sub these things in and we could figure out what are the actual numbers. What also is friction? So in this case, we've got that friction is equal to M2 was 1 kilogram, so F over 1 plus 2, 3. So friction's equal to F over 3, because that's the amount that it has to get. It's the share that the top block has to get, because it has 1/3 of the total mass of the system, so it has to get its equal share for its mass to be able to move at the same acceleration. So the friction has to be equal to F over 3 for the acceleration to be the same between both objects. So what's the maximum amount of friction? Remember that it's going to have maximum friction and maximum static friction, I should say, because we're static here. Maximum static friction is going to be the maximum velocity without slipping. So once again, it's that razor's edge. So the velocity, the minimum velocity for slipping is going to be that flip over point, where the maximum velocity without slipping is going to be the same thing as the minimum velocity of slipping. If we just go over just a hair, just 0.000001, just infinitesimally smaller amount over, we're going to suddenly start to slip. So the maximum static friction is equal to the maximum velocity that we can move at. The maximum force, maximum velocity, maximum acceleration. Actually, I shouldn't have said velocity, maximum acceleration. My apologies. It can, of course, have any velocity. It can be whizzing along through space at, 1,000,000 miles per hour. It doesn't matter, because from its point of view, it's not experiencing any force, so it's about the maximum acceleration. So, maximum force. Okay, so with all that in mind, we're going to have that it will slip at the moment when F over 3 equals max static friction. What's max static friction? Mu s times m2g, or normal force. So if we want to figure out what that is, F equals 3 times mu s times m2g. We just plug in a bunch of numbers now. We use our calculator at this point. 3 times what was mu static? It was 0.7. What was the mass of the top object? It was 1. What's gravity? 9.8. So that gives us that the Newton force, when we use this as a calculator on this, we come up with the number. It's 20.58 newtons. That's how much it is to finally get the thing to just start slipping. If we just barely exceed 20.58, that's the razor's edge, the slightest bit of difference off of 20.58, and it will just start to slip because we'll have just exceeded this maximum static force. All right, great. Hope friction made sense. Make sure, if you've got difficulty with understanding how an incline works, definitely refer to Newton's second law in multiple dimensions. It'll help you get an understanding of how to deal with parallel and perpendicular forces. That's where you want to get that, because it's important if you're going to start working with friction heavily. All right, hope you enjoyed it. I'll see you later. Thanks.